Hi everyone, in this video we will continue learning electronic configuration. We learned how to write electronic configuration first of all. If it's aluminum and you have 13 electrons, you do 1s2, 2s2, 2p6, 3s2, 3p1. We learned that this is energy level 1, that means nucleus, and this is energy level 1, and this is energy level 2, and this is energy level 3. We learned on this page that S, P, D, and F are the orbitals. S has only one orbital, and you can put 2 electrons in it in opposite direction. P has 3 orbitals in it, and according to Hund's rule, you have to divide electrons equally before you pair them up. So P can take 6 electrons, and all those 6 electrons are divided into 3 orbitals, 2 each. So one orbital can maximum hold 5 electrons. So for P, since D can take 10 electrons, so I need 5 orbitals. 1, 2, 3, 4, and 5. So in the 10 electrons go 1 in each according to Hund's rule before you pair them up. And then F can hold 14 electrons, and it has 7 orbitals, 5, 6, 7, and you put 14 electrons in there. So if you have to do electronic configuration, instead of drawing those circles and orbitals, technically this is what you need to do. We know that energy level 1, has only one sublevels. When you say energy level 2, it has 2 sublevels, S and P. Energy level 3 has 3 sublevels, S, P, and D. 4 has all 4, and then 5, 6, and 7, all of them have 4 sublevels. So to do the electronic configuration and make it easier, what I would say that learn how to draw the diagonal lines. So you write all of them like this, and then you draw the diagonal lines like this. And then fill these sublevels based on those lines. Okay. So I'm going to do it again. So energy level 1 has 1 sublevel. Energy level 2 has 2 sublevels. 3 has 3 sublevels. 4 has 4 sublevels. 5 has 5 sublevels. And same is 6. And then 7. So what happens is that once you write all these, you have to draw the diagonal lines. I'm sorry, it was supposed to come through like this. And I don't know why I cannot keep it straight. Let's try it. This one. Okay. So now, let's say you have calcium. You have to do the electronic configuration for 20 electrons. So you're going to start from 1, according to Aufbau principle. We learned about scientists, and we learned that where are their rules according to Aufbau principle. Electrons learn from the energy level closest to the nucleus, which is 1, and then you go to S, and then you go to P, and then you go to D, and then F. So I'm going to start from here. S takes 2 electrons, P takes 6 electrons, D takes 10 electrons, 14 electrons. So let's start from here. You put 2 electrons into this one. So I have 2 electrons here. Then from here you go back to this. So I have 2 electrons here. Then you go to this one. You put 6 in here. You go down, put 2 in there. Then you go to this one. You put 6 in there. You see P. P can take 6. And then instead of going to 3SCP 3D, basically it is telling you to go diagonal. So you have to go down. From 3P, you don't go to 3D. You go down to 4S. Okay. And then you go to 3D. So let's see how many electrons I have had already. So I have 1s2, and then I have 2s2, and then I have 2p6, 3s2, 3p6, 4s2. And if I do the math here, it's 10, 12, 18, 20. it is 20 electrons already. So this is the electronic configuration for calcium, 20 electrons for calcium. So my point is that instead of drawing those energy levels, you have to draw this and then draw the diagonal lines and do the electronic configuration accordingly. So let's do it for aluminum. So you go 1s2 and then you go here 2s2 and you come back here 2p6 3s2 and that is 10 12 and you do only one here. Yeah, that makes it 13. So you don't need anything here. So you do 1s2, after this you see 2s2, 2p6 and then go down to 3s2 and then from 3d you come back to 3p1. So that makes it 13 electrons. So with this you can continue going, fill the orbitals diagonally and continue doing the electronic configuration for whatever number of electrons you have. You just need to keep in mind that S takes 2, P takes 6 and E takes 10 electrons, and this is where you can do the electronic configuration. But the other thing you also need to learn is the noble gas configuration. So noble gas configuration means that we are going to choose the noble gas and replace our core electrons with it. So for aluminum, you have 13 electrons, so 2 electrons are here, okay, 8 electrons are here, so 8 to 10, and the 3 electrons are here. So electrons in the outermost ring are called valence electrons, and everything that's inside, between this and this, 8 into these 10 electrons, they are called core electrons. So for noble gas configuration, I'm going to replace my core electrons with the noble gas, okay. So if I have calcium, 1s2, 2s2, 2p6, 3s2, 3p6, in this 4 is telling you that it's 1, 2, 3, 4. This is the fourth energy level and it has 2 electrons. And this one is the valence electrons. The 2 are the valence electrons and this is the valence shell because they are outer electrons. Outer electrons are called valence electrons. And everything that's inside between the nucleus and that valence shell are called core electrons. So I'm going to replace the core electrons, which are all these, with a noble gas. So how many core electrons I have here? 6, 8, 10, 12, 18. Now if I go to the periodic table and see which noble gas has 18 electrons, I will see that argon has 18 electrons. So if I do the electronic configuration of argon, it will look just like this because it's 18 electrons. So instead of writing this whole thing, I will say argon and I replace it with argon and say 4s2. So this is called noble gas configuration, or we call it core configuration. Okay, core configuration or noble gas configuration. It doesn't mean that you can discount all the inner electrons and replace them with any element on the periodic table. What it means is you only have to replace it with a noble gas. So for example, we have iron. So let's do the electronic configuration of iron. So let's do this. Iron has 26 electrons. So we go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, sorry, and then 3d6. That makes it 26 electrons. So this one is the fourth energy level. Which one is the valence? Okay, shell. And how many valence electrons? 2 valence electrons. So how many electrons inside? You have 18 right here and 18 plus 6. It's like 24 electrons. So I don't have any noble gas that has any atomic number of, just atomic number of 24, because I subtract my valence electrons. I just need to replace my inner electrons. So since I don't have anybody with 24 electrons in the noble gas, so I take the closest one. So wherever iron is written on the periodic table, you just need to see the noble gas right above it. So you will see that if iron is in this period, the noble gas above it is argon. So you just take the noble gas right above it, which is 18 electrons. So I will say argon, argon to replace the 18 electrons. And then I say 4s2, 3d6. I can say argon, 3d6, 4s2. That doesn't matter. But basically it's 18 plus 6 right here plus 2, that makes it 26. So instead of writing this whole long electronic configuration, I only write a small electronic configuration. This is called core configuration or noble gas configuration. So an element cannot be its own noble gas configuration. Like I cannot do the electronic configuration of argon with argon. We're doing it for other elements. Uh, there are exceptions to the electronic configuration, okay, to the predicted configuration, and the exception is copper and chromium. So most stable configuration is the full sublevel, like we like to have 4s2 and we like to do 3d10. That makes it stable, that if s can take 2 it has 2, if d can take 10 it has 10. But sometimes this does not happen. Like for chromium, the noble gas configuration for chromium, so let's write it. Chromium has 24 electrons. Okay. So if I do the noble gas configuration for chromium, the element sitting above chromium is argon. Alright, so that replaces 18 electrons. So let me write it here. Argon, that's 18 electrons. Then I have 4s2, and then I have 3d4. That makes it 24 electrons. Okay. For copper, I can do argon 4s2, okay, 3d9. But the reason that copper and chromium are exceptions, because this is not what their actual configuration is. Their actual configuration is going to be argon 4s1 3d5. So this is not what we have learned so far. We have learned that you have to complete this before you go further on. But as I'm saying, that copper and chromium are exceptions to this rule. So it will be 4s1 and 3d10. All right. So copper will complete the 3d10 before it goes to 4s1, and chromium will have half filled s and half filled d. Partially filled s and partially filled d, which is not stable. This is not stable, but this is how they are. This is why we say that copper and chromium are exceptions to the predicted configuration rules. So keep that in mind, that in all the configurations that I was doing, I was completing the 4s2 before going to 3d10, but for copper and chromium, the 4s is partially filled and electrons are in d orbitals. Alright, so we also need to learn how to do orbital diagram. I don't know if I did this before or not. So let's do orbital diagram for phosphorus, 15 electrons, 1s2, 2s2, 2p6, 3s2, 3p5. So how many orbitals each has? S has one orbital, no matter which s it is. Okay. P has 3 orbitals, no matter which p it is. Okay. So what I'm going to do is now put the electrons in it. I have 2 electrons in S, so I have to go opposite direction. The S, 2 electrons. P has 6 electrons, and I have to go 1 in each before I pair them up. Then S has 2 electrons, and here I go 1, 2, 3, 4, and 5. So this is called orbital diagram. Orbital diagram. This is called, this is called electronic configuration. And if I want to do the noble gas configuration for phosphorus, what would that be? For noble gas configuration, I will replace the core electrons. These are my valence electrons, right? These are the valence electrons. So I will replace my core electrons with the noble gas. So if I look above phosphorus, I will see neon. So neon will replace the 10 electrons right here, and then I will say 3s2, 3p5. So this is the noble gas configuration. So you need to understand the difference between noble gas configuration, the actual standard electronic configuration, and orbital diagram. So this completes all the information that you need to learn on electronic configuration. Make sure you practice all the questions, and you should know all the scientists, you should know all the sublevels, you need to know how many electrons go into each sublevel. So if you have any questions, let me know. Thank you very much, everybody.